Hello and welcome to this vodcast on atomic and nuclear physics. I think this is the third vodcast in the series, and we're going to look today at the nucleus and just at the nucleus. So covering 3 assessment statements, but hopefully won't be taking too long about them. Oh, neutron number n. Oh, that's easy enough to do. So the nucleus. We know that it's got about a size of 10 to the minus 15 meters. That's for a small nucleus, to within an order of magnitude. The largest nuclei can get maybe more towards 10 to the minus 14. We know it's got a positive charge, and we know it has almost all of the mass of the atom. The figure for hydrogen is 99.946%, and that is the figure where the nucleus has the element for which the nucleus has the least amount. Okay, so for all other elements in neutral atoms, it's going to be bigger than that. We know that there's a unique number of protons for each element, and we know that nuclei of the same element can differ in mass. So what's our evidence for this? This, by the way, is a picture, but it's not a photograph. It's actually a simulation, a prediction of the structure of a nucleus. So it's on the femto, which is 10 to the minus 15 femtometer scale, and looking at what does a nucleus actually look like? Is it more of a collection of the protons and neutrons all in one place, or is it more of a sort of liquid drop model? And the answer seems to be somewhere in the middle, but we'll be looking at that in more detail maybe later on. What evidence is there for the mass of a nucleus? Well, by various nefarious means, we can kind of weigh a nucleus, and what we find is that the mass of all nuclei are approximate multiples of the mass of a hydrogen nucleus, which is the lightest nucleus that we know of. One way to think of this is like a bag, and inside the bag there are a variable number of marbles, all of the same type. And what we find is that when we look at each bag, there's sort of one division, and every bag will be, the mass of the bag will be a multiple of that division, and the smallest division is the hydrogen nucleus. So, if we have 3-4 different atoms here, then there will be an exact multiple, or almost exact multiple of the number of hydrogen atoms inside the bag, in terms of mass, at least. If we look at charge, we get a similar but slightly different story. The charge of a nucleus is also a multiple of the charge on a hydrogen nucleus, which we know now is a proton. But we notice that it's not the same pattern as the increase in mass. So you have hydrogen, and you have some varieties of hydrogen, then you have helium with a mass of 4, and then you have different elements, and the number doesn't always go up, whereas the charge does always go up by the same each time. 1, 2, 3, 4, 5, 6, etc. Same is not true of mass. There's a different ratio, and the solution to this mystery is that we conclude that the nucleus contains 2 different kinds of particles. One positive, which carries the charge, and one neutral, and that they both have the same mass. We call that mass 1 atomic mass unit, which is the symbol U. So that's kind of our basic model of mass and charge of the atom. And here are some examples. So hydrogen, 1 proton, and then you have something that has the same charge, but the mass is increased, which we call deuterium. And then we have something with the same charge again, but the mass is increased by once more, and that's the substance called tritium. And then we have helium, which has 2 charges and the mass of 4, but there's also a variety of helium which has 2 charges and a mass of only 3. So what are the quantities and the properties of a nucleus? Well, this is a basic extract from the periodic table, which you should be familiar with. The symbol C, the actual element name might or might not be there, carbon, and these 2 numbers, 12 and 6. Well, the biggest number is always the atomic mass, the mass number, nucleon number, which is given A, or mass number, and that gives you the total number of protons and neutrons, which are the neutral particles and the positive particles, inside the nucleus. The atomic number, atomic mass number and atomic number are 2 different things. proton number is given as symbol Z, and that is the number of protons, and that determines the element. It's carbon because it's got 6 protons. Okay, not the mass, because that can vary, but the 6 protons of carbon are what make carbon carbon. The other thing it just did mention, if I go back into the assessment statements, is define neutron number, n. Well, in all my experience we don't really use that, but the neutron number is simply the number of neutrons, and you would find n by taking the atomic mass, A, and subtracting the number of protons, because that's the number of protons plus neutrons minus the number of protons. So A minus Z will give you n, the neutron number. So we namely give to different atoms which are the same element but have a different mass is isotopes. And there are 2 families of elements here. Hydrogen, deuterium and tritium are all one family. They're all varieties of hydrogen. Okay, they just have special names. They're all hydrogen because they all have 1 positive charge. All that varies is their mass. 0 neutrons, 1 neutron, 2 neutrons. And the other is helium. This is standard helium and helium-3, called helium-3 because it has a mass of 3 atomic mass units. This, properly called, we should call it helium-4. We don't normally, because most helium, the vast majority of helium is helium-4, but if we wanted to distinguish it from helium-3, then yes, we should call it helium-4. So rearrange these into the 2 families. Here is the family of the hydrogen isotopes, and here are a couple of helium isotopes. Here is the data as you would find it on a variant of the periodic table. The atomic number or proton number stays the same every time, Z equals 1, but the mass number goes up by 1. 1, 2, 3, A equals 1, 2, 3. That's how you'd find it on a sort of periodic table type arrangement. If you are writing this down, you would write it down using this symbology. So here we have 2 isotopes of carbon, carbon-12, which is the standard isotope, and carbon-14, which is a radioactive isotope that we'll be looking at later on in the course. And we write C as the atomic symbol, but we also write the proton number down here, bottom left, which is 6, and the mass number at the top left, which is 12 for carbon-12 and 14 for carbon-14. Now, one little problem, if you look at a nucleus, is that you have a large bunch of positive charges all stuck together. And so the positive charges really want to repel each other. They have electrostatic repulsion. They're pushing each other apart. Something must be holding them together. And the thing that's holding them together must be stronger than the electrostatic repulsion that's trying to push them apart. Which makes it pretty strong indeed, because electrostatic repulsion is a lot stronger than, say, gravity. Gravity is a very weak force, and at the scale of the atom it has no effect whatsoever. Electrostatic repulsion has many effects, but this strong force found in the nucleus is even stronger. It's the strongest force that we know of. It's able to hold these protons together, even though they really want to push each other apart. It's a strong force, it's found in the nucleus, so imaginatively it's called the strong nuclear force. It has a very short range. In fact, it switches off outside the nucleus, which is very weird, and is the first sign that in this realm of physics maybe things are not the same as they are elsewhere in the physical world. It is the strongest force of all. It affects all nucleons equally. Protons attract protons, neutrons attract neutrons, and protons and neutrons attract each other. The exchange particle is given the slightly silly name of gluons. An exchange particle is the particle that carries the force. Every force can be thought of in itself as a wave and a particle. So the exchange particle for the strong nuclear force is gluons. Okay? For electromagnetic radiation, it's photons. For gravity, it's gravitons. Okay, but gluons, which glue the nucleus together, is the exchange particle for the strong nuclear force. And that actually concludes our vodcast, our slightly shorter vodcast on the atom. Okay, we'll look in more detail about the energies involved and about what happens if your ratio of Z to N is not appropriate in the next set of podcasts. Thank you very much.